the flux integral. We want to calculate here the amount of fluid flow through or along the surface. The surface must be an oriented surface. That is, that if the fluid flow is flowing across or on top of the surface, we want to keep it like that. Here we examine the continuity of the so-called vector field, because of which that's the direction that the fluid is flowing in. To calculate this fluid flow, we're actually calculating the volume of the height of a beam here as the fluid is flowing through across the surface. This volume can be approximated here by the height and the base area. The height is calculated as the dot product of the vector field with the normal vector, and then the base area is the change in S. So here this volume of the fluid crossing the surface as per unit of time is called the flux of F over or across S. This flux integral here is based on capital F, some vector field, where the components M, N, and P are continuous. They have continuous first partial derivatives along the surface. S, and then here S is said to be oriented by some unit normal vector capital N. So the flux integral is the double integral across F. Here F dot N again is the height, and then ds calculates the base area. Pictorially, this is what we have. F dot N is the height. You have the surface, and then you have the fluid that's flowing here in the direction that's given, and then the base area delta S times the height F dot N gives you the volume. Now, to evaluate the flux integral, we're going to use this setup. Now, what is this setup? Let me see if I can explain it for you. This is the double integral. It's reduced to across R, dealing with values in the xy plane. This is actually F dot with the gradient of G dA. Now, I wonder if you see that, and let me explain that in detail for you. And so what I'm saying, this is the only thing that I use. I don't use all of this stuff. Too much stuff to remember. I cannot remember a lot of stuff. So you want to be able to calculate, maybe I should start with the first term. Here, the dot product of F and N, and then ds, not dr, not da. I think I was about to write that. So this is F dot with. Now N is the gradient of G divided by the norm of the gradient of G. And ds, you recall, is the norm of the gradient of G times dA. So here the norms cancel out. This is F dot with the gradient of G dA. Here where N is equal to this gradient of G divided by its norm. It's the unit normal vector. And ds is equal to the gradient of the norm of G times dA. So I think, well, with that in mind, we have this flux integral, which is this double integral over the surface, the dot product of F and N ds. I reduce this to the double integral over the region of F dot with the gradient of G dA. That's what I use. So let's see. Here, find the flux of F across or through S, where N is the unit upward unit normal vector to S. So I need first G. G is Z minus G of XY. This is Z plus X plus Y minus 1. This gradient of G is the partial with respect here to X. This is 1 times I plus the partial of capital G with respect to Y, and that is a Y, which is 1 times J, and then the partial of capital G with respect to Z, which is 1 plus K. So we need that. Now capital F in terms of X and Y, where here Z is G of XY, this is 3 times Z is 1 minus X minus Y I minus 4J plus YK. Now we need to define the region R. So for the region R, let Z equal to 0. When you do that, we have 0 is equal to 1 minus X minus Y. That is, Y is equal to 1 minus X. So it's first octant, so Y goes from 0 to 1 minus X. If you let Y equal 0, this implies that we have Y equals 0 here, so we have 0 is equal to 1 minus X. This implies that X is equal to 1. So the domain for X would go from 0 to 1. So our region is 0 less than or equal to X less than or equal to 1, then 0 less than or equal to Y less than or equal to 1 minus X. Here R is restricted to X and Y. So this flux becomes this double integral over, just keep this as R for now. This is the dot product of F with the gradient of G dA. We have the gradient of G. It's this guy here. So capital F is here. This is 3 minus 3x minus 3y I minus 4j plus yk. That's dot with the gradient of G. This is I plus j plus k. And this is dA. Now we can go ahead and put what you want in there for these limits of integration. X goes from 0 to 1. Y goes from 0 to 1 minus x. Take the dot product. We're going to get 3 minus 3x minus 3y minus 4 plus y. And then this is dy dx. simplify this. The integral from 0 to 1, the integral from 0 to 1 minus x. 3 minus 4 is -1. Then we have here, this is minus 3x minus 2y dy dx. So integrate with respect to y. So we have negative 1 times y. Why is this pen not wanting to work for me? Minus 3 times x times y minus 2y squared divided by 2, which is just y squared. Here y is evaluated from 0 to 1 minus x. And here we have dx. This is the integral from 0 to 1. Replace the y with 1 minus x. So this is parentheses negative 1 minus x minus 3x times parentheses 1 minus x minus 1 minus x to be squared. Oh, there's no 2 there. We dealt with that. 1 minus x to be squared. Evaluate at 0, then all the terms go out. Need to simplify all of this. This is the integral from 0 to 1. This is minus 1 plus x minus 3x plus 3x squared. This is minus 1 plus 2x minus x squared. I think I got that all right. Did that FOIL and negate it at the same time, right? So let's see. I'm still simplifying. This is -2. We have x minus 3x plus 2x cancels out. We have 3x squared minus x squared, which becomes plus 2x squared dx. Integrate. We do not hesitate. This is -2x plus 2 over 3x to the third. Evaluated from 0 to 1. So that leaves us with -2 plus 2/3. That gives us -4/3. What was that? Hello. As Tyler Perry says, the devil is a liar. Mama said it too. But anyway, so here the fluid flow is diminishing, it's negative, right? So now let's look at another one. I need capital G. Capital G is this z minus all of this. So it's plus x squared plus y squared minus 1. So the norm of G is equal to, the gradient of G, excuse me, is 2xi plus 2yj plus k. And then capital F is xi. Everything must be in terms of x and y. The z based here on x and y. Z depends on x and y. So this is xi plus yj plus z, but that's parentheses 1 minus x squared minus y squared. Okay. Now, what's the region? Find R. You have to let z equal to 0 here, and so that gives you 0 is equal to 1 minus x squared minus y squared. That is x squared plus y squared is equal to 1. So this implies that the region has definition. It's the circle. All right, so here the radius is 1 and it's a complete circle. So theta goes from 0 to 2 pi. So we have this double integral over the region. The function f is xi plus yj plus parentheses 1 minus x squared minus y squared k, dot product with the gradient of g, 2xi plus 2yj plus k, and this is dA, double integral over the region. This gives us, do the dot product or do the hustle, do the hustle, 2x squared plus 2y squared plus this times 1 is 1 minus x squared minus y squared. I'm getting hungry. Oh man, looks like stuff is crawling on my desk, but it's not. So that's a sign that I'm hungry. It's time to eat lunch. Okay, it's 2:14 p.m. and I haven't had lunch, but that's no problem. So this, we simplify this. This is 2x squared minus x squared is x squared plus 2y squared minus y squared is y squared. Then this is plus 1 dA. I'm going to convert now to rectangular, from rectangular to cylindrical or polar coordinates, however you want to say it. So x squared plus y squared is r squared plus 1. This is times r dr d theta. R goes from 0 to 1. Theta goes from 0 to 2 pi. Simplify that again. This is r to the third plus r dr d theta. Okay, so we integrate. So we get 1/4 r to the fourth plus 1/2 r squared. Evaluate the r's from 0 to 1. This is d theta. So that's just 1/4 plus 1/2 on the outside times the integral from 0 to 2 pi d theta. That's just 2 pi, right? So here we get 1/4 plus 2/4. That gives us 3/4 theta. Theta is evaluated from 0 to 2 pi. And that gives us 3/4 times 2 pi. So it gives us 3 pi over 2. Okay. All right. Let's look at one more. And then we're done with this, this section. All right. So nothing to convert for f is defined as 4i minus 3j plus 5k. But what about capital G? This is z minus x squared plus minus y squared. I'm going to convert this to z minus r squared. And so we can get our gradient here with respect to r, theta, and z. So this is negative 2r I plus k, right? There's no theta there. And what about you see this is a circle, complete circle with radius 2. So R goes from 0 to 2. Theta goes from 0 to 2 pi. Let's make sure that this works with this gradient defined here in terms of R squared instead of x squared minus y squared. Let's see how it works out, and if we have to go back and fix it, then we will. This is part of my theory, by the way, just going ahead and converting quickly to the gradient. You know, the author doesn't use this as much. I used the gradient of g from the very onset of our discussion. So anyway, this is the double integral. Here we got to have f is this is the double integral, converting into the region. This is f dot with the gradient of g dA. This is part of my information. So this is 4i minus 3j plus 5k dot product with negative 2ri plus k. I wonder how that would work. Let me go back. I need to probably work that also 2 ways to see if they both come out to be the same. That's interesting to see. I'll be safe to don't convert so soon to R. And so the gradient of G is negative 2xi minus 2yj plus k. Be safe to use that. So this is negative 2xi minus 2yj plus k. This is with respect to dA. This is over the region. So now let's do that dot product. It gives us negative 8x. This gives us plus 6y plus 5. Guess we can go ahead and we'll leave that here. Let's go ahead and do the conversion now. So this is the double integral. This is negative 8r cosine theta plus 6r sine theta plus 5. You know, for the cylindrical coordinates, you got to have r, then a dr, d theta. R is going from 0 to 2. Theta is going from 0 to 2 pi. I'm seeing 0 for the cosine and sine. So since I'm seeing 0, look, we're going to take the integral and then evaluate on a complete circle. So with some conservation in there, we're going to get 0 in our energy flow. So here's what I'm going to do. So we're going to say this is from 0 to 2 pi, and this is from 0 to 2, and this is d theta dr. If you can see that, fine. Use it. Integral from 0 to 2, integral from 0 to 2 pi. You got to run that r through there. So it's negative 8r squared cosine theta plus 6r squared sine theta plus 5r d theta dr. Okay, so let's see. We're going to integrate with respect to theta. So this is the integral from 0 to 2, and this becomes negative 8r squared sine theta. No, the integral of sine is negative cosine. The integral of cosine is positive sine. This is minus 6r squared cosine theta plus 5r theta. Theta is evaluated from 0 to 2 pi. This is dr. Now, see if you can help me so I don't have to do all the writing. You evaluate sine at 2 pi, that's 0. Then minus, you evaluate sine at 0, that's 0. So this is 0, right? Evaluate cosine at 2 pi, you get 1. Minus cosine at 0 is 1. So isn't that 1 minus 1, 0? See that? Make it light on yourself. So that information goes out. So the only term that you evaluate in terms of the theta would be this 5r. So this is the integral again from 0 to 2. Here we have 5r times 2 pi and then dr. So we get 10 pi sitting out in the front times the integral from 0 to 2 of r dr. So this gives us 10 pi r squared over 2, and the r is evaluated from 0 to 2. So this is 5 pi, and then here the r is 2 to be squared, gives us 4 times 5, 20 pi. Now I wonder what would happen if you make that conversion early like I was about to do, to see if we would get 20 pi. Well, I'm going to break now and eat my lunch, and then maybe while I'm eating my fajita, I may do it on the side, okay? If it works, I may make mention of it in my opening for 15.7 lecture. But if not, hey, who cares, right? You got it. Thank you.